Okay, so there's a pretty elementary package that you should be fine with for a while in R. Let's actually make sure we go over this next time in class also too, but I wanted to show you just, I dug up in my consulting files and found an actual power calculation and then added an example just for explanatory purposes. The package in R is called PWR for power. And this is actual data from a pilot study that occurred here on campus. I got the data from a researcher. He was planning a proposal to NIH. And so this was the power analysis I did. So this is preliminary pilot data. That's really best case. I love it when I get that kind of pilot data from a researcher. So I got it in kind of a strange format, and so I had to enter it in kind of a funky way here, but ignore that for now. I have pre-test scores and post-test after an intervention was applied. Okay, so I calculated here, take a look at the base here. Took a sample from that baseline score, and then the second sample from the post. And so this just gives us a resampling of the data. I like to use this personally. I can run this multiple times and see how consistent my results are. I wanted to test for an effect. The investigator really didn't have an idea about what kind of effect size to look for. And so we're looking for an effect that would be 10% above what we saw. So I did kind of a strange calculation here. Don't worry too much about that because that's very particular to this case. And then we calculated, or I calculated, a t-test at the interval particularly to estimate that effect. So this kind of gave me a sense that 3.68 up to 52 something gave me a sense of what kind of effect size I could anticipate to see for that 10% increase in response. Okay. Then I pulled the standard error. Again, just a very routine calculation there. I just used a very, a home hand done formula there rather than anything else because it's so simple. This is the absolute deviation then, using that pulled standard error for scaling. And now we can finally get to the point where we can use this power for t-test function. And this is really nice. Mostly, it's not a hard calculation to tell you the truth, and I could easily script it in R. But what's nice is this package gives you the ability to see power curves if your collaborator wants to see something like that. So notice I use the function power t-test. You have to kind of think about, well, what's the scale? I went way too high here, I would say. Let me think. Maybe up to 80, I'm thinking. I'm going to change that from 110 to 80. I did this so long ago, I honestly can't remember why I used such a high level for the sample size, but you go from that sample size up to that, okay? I'm using less than as an alternative because that was what the investigator needed. I can run that function and we get all these numbers are the estimated power. So at n equals sample size of 15, I get 40%, a little above 40%. Up to n equal 80, I get 95% power. I guess that's why I went up to 110, because I wanted to see how I could get near 100% power. So let me run that again. I always question myself when I go back over my code, but actually, yeah, I like what I originally did now, because this goes up to almost 100% and I'm at 99% power. So you kind of get a sense of the span of powers that's obtainable at different sample sizes. There's a second calculation where now the significance level changed from 5% to 10%. So in case they want to entertain that, so you can see we do increase our power if we change our significance level. Then you can do a plot. Notice one of them's just over here. This shows you as your sample size increases, and as on the x-axis, your power increases. So the investigator can even draw a little line here, and in fact, for some reason it's not drawn. There we go. So say you want a line at 80% power, then you can just extrapolate. That's about 40. Sample size about 40 to get 80% power. Okay. I think this is the same. Yeah. Oh no, this is the second. This is with 10% significance level. So we need a little less samples if we are willing to tolerate overall type 1 error of 10%. This is using a Cohen's d. So if I included this only because, especially if you are working with social scientists, they'll say, well, I want to be able to detect an estimated difference that is at least 0.2 using this effect size measure of Cohen's d. And so this is how you'd put in, this is very generic, but this is how you'd put in that kind of a calculation. So you can see if I run this code, it says, if my sample size is 60, and I want to detect a difference with Cohen's effect size d equal to 0.2 or greater, and my significance level is 10%, then I have a power of about 45%. I think I had done this for somebody because that was actually what, oh no, this is from an exercise in Cohen's book. That's right. I think I was looking that up for somebody to see how to do this at one point in my life, and so I just included that for an explanation too. Going back over all my power calculations, or some of my power calculations. So we can talk about how to modify this for class. Later we'll get to the simulation base too, a little bit in more detail. But notice here, let me just go over this one more time. If I resample, we're going to get very, very similar. It's not identical results from before. And we get, again, very, very similar results overall. Okay, so that just adds some validity to our power calculation.